if you relate some of these bases with the nth roots and all that stuff, if you're able to relate them back to stuff you know, your rules for adding, subtracting, multiplying, dividing, whatever with your exponents, if you're able to get things within the same bases, more often than not, you're going to be able to solve the problem rather easily. Granted, there's going to be a fraction here or there. I do know that some of the stuff that I do, I'm kind of going a little bit of a longer way on some of these problems by going about that route, which is fine. It's also preparing you guys to be able to do logarithms later. When we work with logarithms, logarithms are nothing more than bases and exponents. They're kind of boring, I know. But they work out cleanly if you understand how you're able to change bases quickly. So let's just get started and show you guys kind of a little bit of the trick here. Now I know that there are going to be multiple ways to set up. Oops. This one's rocking out too much.
That one was easy. It just came out to be 5.
Right, but I would show why. Now in this case here, do they have the same exponent?
Yes.
Yes. They're not the same base, but it is the same exponent, which means you could rewrite this as this. Well, let me just do it this way. As 70 over 14 to the third. Okay. 70 over 14 simplifies to be 5. So this is 5 to the 1/3 power. You're done. Exponents don't drop, they still stay there, you're just simplifying the value. Now, if this has come up a couple of times throughout the day today, the etiquette of these problems are if you start with a fractional exponent, finish fractional. If you start nth root, finish nth root. To be honest with you, I like to switch things to fractions. I think it's easier to see how things work as opposed to nth roots. See, I do a lot of it that way. Is that what you're going to ask? I saw you nod. So yes. Clay, was that you, or what do you have?
I was going to ask, like, what if happens if, like, a problem? Because I had this where you have radicals above and radicals on the bottom. You changed all the fractions, but when you play war, you get something like.
Do you have the same base with those fractional exponents, though?
What do you mean? Like, because I had.
They have to have the same base to play war.
See, this is what I got, because I had like 41.
Let me get to it, okay? Let me get to it.
Because I tried to transfer them in fractions, but make it like, just have the same bottom denominator so they can cancel out, but it's weird.
Stick with me, kid. I'll help you out. I don't mean, like, I was stick with. There's a line in a movie. Stick with me, kid. You'll go places. I forget what that was. Was it Casablanca? What's that?
Oh, yes. Simone and Tumbo.
Yes, Simone. Yeah. Simone was the girlfriend in Paris. See, it's not just a math class, it's a multicultural experience. That's deep. Wow, that was a lot of BS there, wasn't it? Now, in this one, we go into number 30. We don't have the same bases, but we have all the same exponents. Since we have all the same exponents here, just rewrite it as one giant fraction. You get 20, you end up with 24 over 3, wait, yeah, which is 8. So you get 8 to the 2/3.
Wow.
Now, at this point, you need to recognize something that you have a 3 for a denominator of the fractional exponent, which means it's a cube root. Can you find the cube root of 8? Yes, sir?
I did it wrong and got it right. I divided them out and played war.
That's fine, but here's the problem with that. They don't have the same base, you can't play war.
War became 4/3 over 2/3. It's like a deck of cards.
You really can't do that, all right? Now, here, what I'm hoping that you guys will start to recognize is that when you have these cube roots with some of the perfect cubes. Rewrite this, you can say it's the cube root of 8 squared. So what's the cube root of 8? 2 squared is? You have to be able to do this without a calculator. Okay?
So you like to play more things the A's are the same.
we have to make them the same. I'm gonna get to that. There are ways of doing that. I think it's the next one. Yes, ma'am.
Oh, wait, are we telling you problems or are you just doing stuff?
I'm doing some in here. Let me.
Okay.
What I'm trying to do, I'm trying to get at through a couple of them in each grouping here throughout these. Like in 31. Oops, that didn't click very well. Let me try that again. When I'm looking, I knew I was going to do that. When I'm looking at 31, my numerator and my denominator don't have the same base, do they? No, but my numerators do. Does everybody see that?
Yeah.
So, since they have the same base and they have different exponents, what do I do with their exponents? I add them. What's 2/9 plus 1/9? 3/9, otherwise known as 1/3. So is everybody okay by saying this is 125 to the third?
Yeah.
What's 125 to the third?
5.
5.
It is 5.
It's the cube root of 125.
That's crazy.
Which becomes 5 to the first power because it has an exponent of 1 that we just don't write. And then denominator now is the 1/4 still. And now we go back to play the game of war. Now you have you have the same base, different exponents. Who wins? A 1 or a quarter?
That's what I was trying to do. I just got away from it.
So now what?
What's 1 minus a quarter? Yep. And once again, since they started this as a fractional exponent, we just fill back to the fraction. Now you gave me the look up like, huh, oh, we did. This isn't that bad.
How come that do the 1/3 of 125 and you're necessarily at the bottom?
Because I can't do anything to it. I'm looking at this, that can't be simplified. What's the 4th root of 5? I don't know. But I do know what the cube root of 125 is. There will be times that you have to simplify bits and pieces, just like when we worked with square roots before. If you had the square root of 12, you knew to simplify it as 2√3. 18, 3√2, things like that. You would catch those little nuances as you go through, all right? Now, in the next grouping, you're starting to deal with them more in terms of having them written out as nth roots. You have the square root symbols in there, the radicals, if you will.
55 was made up the other ones. That's pretty easy.
As you go through, what I want you to remember here is the value underneath the radical is your base. So in that first problem, aren't those the same base? But they're different exponents, aren't they?
Yeah.
So if you go back, and this is where I was saying, sometimes it's cleaner and easier to rewrite your nth roots as fractions. So this is 64 to the half, and this is 64 to the third, correct? Oh, wait a second. What's the square root of 64?
8.
What's the cube root of 64?
4. I just jumped right to that.
That's fine. But it works the same way. Sometimes just give yourself a high five, error 5 for your own error 5. I swear to you. A lot of times it works like that. You might not catch it right off the bat, but as you start to fill in the blanks, you're like, oh wait, I can do that.
Yeah, we can do that.
This may be a sweet question. I want to know if you're like solving or simplifying, because that looks like solving.
You're simplifying.
Equal.
Solving is there's an equal. Yeah, exactly. Solving is you're solving for something. Simplifying is you're just working through. Okay?
What was the answer then yours?
I don't know.
It was 5 3/4.
5, 3, 4, 6. Now, when I go to the next one, I don't have that same base. But can I convert 8 into a base 2?
Oh, yeah.
8 is 2 to what power?
It's 2√2.
It's 2 cubed, right?
Yeah.
You okay with that? So here's what I'm going to do. I'm going to write this as, first I'll do 8 to the 4th times 2 to the 4th. This 8 I'm going to rewrite as 2 cubed to the 4th times 2 to the 4th. Does everybody agree when I multiply? What's wrong with you? Sure? Okay. Is everybody okay? What's wrong, John?
Okay.
All right. If I multiply those two together, I get 3/4. So this is 2 to the 3/4 times 2 to the 1/4. Same base, different exponent. You're multiplying when you do the exponents. What's 3/4 of 4? What's
I got that wrong.
everybody just went, wait, what the? What?
Can't you just do 8?
Just wait, what the what?
Same answer.
Yeah, you do that too?
It makes me feel like I was wrong.
No!
Why can't you?
What I'm saying here is, I'm trying, you guys did that fine. You multiply them together because you have the same nth root, that's fine. Sometimes it doesn't work that clean. All I'm showing you is that the long way isn't the wrong way. It still works, okay? It still works.
Yes, they're multiplying the right, but the wrong one's another way.
It is, but you have to be careful. If it was like 8, the 5th root of 8 and the 4th root of 2, you can't do that.
I know.
Just making sure on that, all right?
Can you go over 36?
No.
Rewrite as fractions and distribute.
41.
38.
Now, in this case here, we have the same base, but we have different nth roots. Are we okay with that?
Yeah.
I'm going to rewrite these as fractions again. That's 7 to the 1/2, and that's 7 to the 1/5. Same base, different exponent, and you're dividing. You have to play. Who wins, 1/2 or 1/5?
1/2.
1/2.
Wait, you can do that even
Yeah.
if they don't have the same fraction?
Yeah, because it doesn't matter about the fraction, it matters about
The
the
base.
base.
All about that.
Base. All these stuff.
It's all about that.
It's all about the base.
So now, when you're doing work with these, you just gotta get a common denominator. What's common between a 1/2 and a 1/5? 10. So this is 5/10, and this is 2/10. Who wins?
That's
Over
two.
10.
2 or 5.
Who wins? What's 5 minus 2?
7.
So you get 7/3. Now,
Wait.
He did not do that one.
am I done with that?
No.
Why am I not done?
Because you started with the roots.
I started with the roots. Picking that up.
And we go back to the roots.
You're mean. You root up.
Oh, we have one.
Yes, sir. Because we started with an nth root, you gotta finish with an nth root. Okay? That, we're getting it. That is the proper etiquette of setting that style up. Okay? Yes, ma'am.
Yeah. I have one over
No, because you have to work with fractions. I mean, because if you did that, you have the second root over the 5th root. The answer is 1 over the 3rd root. You could do that, but then you'd have to rationalize your denominator. If you rationalize your denominator, you'd get what we got. Okay?
So we just leave it like that?
Yeah. 39 and 40 should have been pretty easy because those guys all have the same nth roots. You can simplify your fractions and then go from there.
40 was 8.
All right, those should be easy to go with.
I got 42.
Okay. You wind up with 1 over the cube root of 8, so you wind up with 1/2.
Yes.
On the other one, you wind up with, what was it, 64. The 6th root of 64, which is 4. I'm sorry, 2.
4.
6th root of 64.
Oh, I see what I did there. I did not write.
That's 4.
I see.
This is 6th root. Two times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 60, is 32, times 2 is 64. 2 to the 6th power is 64. Okay?
And
Yeah.
that's probably to be 41.
I don't know, I haven't gotten there yet.
That's one problem. Well, thank you.
I did not do that one at all.
That's just so long.
What? Which one?
It's the half.
Half. 1/2. Because they have the same nth root, it simplifies out to be 1 over the cube root of 8. Here, two things you can do. First thing you want to work with is work with your numerator. You have the same nth root, so multiply them together. You get the cube root of 54. In the denominator, you get the 6th root of 4. You okay with that?
Yeah.
At this point, there's really nothing that you can do. So, let's see if you can simplify 54. What is a perfect cube that goes into 54? 27. This can be broken down as the cube root of 27 times the cube root of 2. What's the cube root of 27? So your numerator is going to get 3 cube root of 2. Denominator, I need to work with that a little bit. I'm going to do this. I like working nth roots, and when I start messing around with my nth roots to my exponents, to try to simplify things through, I always like to switch to fractions. I think it's easier. This is 4 to the 1/6. You okay with that?
Yes.
4 can be rewritten as 2 to what power? 2. So this is also the same as 2 squared to the 6th, which is 2 to what power?
What's
2 to the 3rd. How do you multiply fractions? You multiply them together. 2 times 1/6 is 2 over 6. 2 over 6 simplifies to be?
1/3.
Your answer is
Wow.
3.
Oh,
That is so
that's what I got.
I
6 to the 4 by 2. Guys, hold on, I can't hear. It's done what? Okay, not always it's gonna look, it's not always gonna be that clean. It's not always gonna be that clean. What happens there is, the reason why I wanted to break that 4 into a base 2 is notice that your numerator has a base 2 in it. That gives you the clue that you might want to go to a base 2. It's these little nuances as you start to do more and more of these, the more you break it down to a prime number, to an exponent, the easier a lot of these become. Right? A lot of them become easier as you go through this. And the same idea when you start to get to the ones where you have to rationalize, like in 46. As I get into number 46, I've got the cube root of one giant fraction, 1/7.
We didn't do that. You told us not to do that one.
I know, we're going to do it now, because this is the important stuff for today.
important stuff for today.
Because you'll have to do this later on. Does everybody agree that this is the cube root of 1 over the cube root of 7? What's the cube root of 1? Okay. Are we okay with that? All right. At this point, I don't want a radical in my denominator. The easiest way to alleviate this issue is to switch it to a fraction. The cube root of 7 can be rewritten as what? 7 to the 1/3. Good. Now, let's go put a pause on this spot and remind you guys how you did this. What did you do? Multiply both by root 2. So you get 3 root 2 over 2. Agreed? That's how you rationalize the denominator. Now, in terms of a fractional exponent, isn't that 3 over 2 to the 1/2? Times 2 to the 1/2 over 2 to the 1/2. Same base, different exponent. What did you do to the exponents? You add them together, right? What's 1/2 plus 1/2?
1.
You created a power of 1 in the denominator without realizing that's what you were doing before. By working with square roots are half powers. When you're multiplying two numbers together that have the same base, with a different exponent, you add them. 1/2 plus 1/2 is 1. So what we're doing here is we're creating I need to turn that denominator to have an exponent of 1, which means I have to multiply it by the same base, but how much do I add to a third to make it 1? 2/3. 2/3.
Let's do that.
Because isn't this value still 1? Remember, when we multiplied these things out by √2 over √2, we were multiplying by a factor of 1. And it doesn't change it. It just changes the way it looks. So now what's 1 times 7 to the 2/3?
7 to the 2/3.
And now I just have to rewrite it back to the nth root. By going back to the nth root, then you get the cube root of 7 squared all over 7. And you're done. You no longer have a radical within the denominator. You have no fractional exponent in the denominator. No, you can't play war here because if you played war, you wind up going back to this. All right? You wind up going right back to that, and you don't want that. All right?
I was blind.
47, same basic idea. Same basic idea here, because we're going to simplify that denominator. And in order to do that, well, we're going to try and simplify it first. It's always easier to simplify the denominator when you get it down to a prime base, a prime, prime base with an exponent. If I'm looking at 81, isn't 81 9 times 9? So if it's 81 is 9 times 9, isn't it also 3 times 3 times 3 times 3? So is 81 3 to what power? 4. Okay. So here's what I'm going to do. Right away, I'm going to write this as 3 to the 4/6. You okay with that? This is the 6th root of 3 to the 4th.
Oh, that makes sense, yeah. Oh, that makes sense.
All right. 4 over 6 simplifies to what? 2/3. So now I have 2 over 3 to the 2/3. And I need to make that a whole 3. What do I multiply top and bottom by? 1/3. And at this point, since we have to go back to rewriting it as an nth root, can I just write it as 2 cube root 3?
Yeah.
No, yeah, yeah, no.
Yeah. Maybe. Yeah.
This, I'm not. Remember when we did this? No, because they have different bases. Remember when we did this? Oh, wrong one. Where was it? Remember when we did? It's okay. Remember when we did this? 3 times the square root of 2 was just 3 root 2, wasn't it?
Yeah, but not you.
Well, what's 3 times 2 to the half? It's still 3 times 2 to the 1/2. It means the same thing. The nth root and a fractional exponent are identical. It's just written in different form. These two things mean the exact same thing.
But that one's just 3 over 2.
No, it's not, because you still have this over 2 here. Okay? When you rationalize out in the past, you multiply top and bottom by what here? Okay. Nothing disappeared there, did it? No. Same basic idea here, where, somewhere here. It's the same basic idea when you're working this. Are you okay going 4/6? Are you okay that becomes 2/3?
Yeah.
To make a 2/3 into a 1, we have to add a third to it. Do you agree?
Yeah, I get that. I don't get the top, like, why aren't you doing 2 times 3?
I'm,
Because 3 has to be
Be-
3.
But you could make
Because-
it 2 times 3 thirds.
this is,
3/3.
it's 2 times, there.
Why
It's-
isn't it just
No,
2 over 3?
the 3 is
It is, when this multiplies through, it is 2 times 3 to the 1/3 all over 3.
it follows the
I-
M over
Why
N.
am I writing it like that?
Because the rule is, we started with that, the root. I have to finish it as 2 cubed root 3 over 3. That's the etiquette way of doing it. Since it started with an nth root, it's got to finish with an nth root. Is that more clear? All right. Sir?
What stops you from writing 2 to the 3/3 and make that 6 to the 4/3 and then 6? Because that's a different answer than 2 cubed root 3, isn't it? Because like you can give that 2 because it has the exponent of 1, right? And then you make a common denominator, you add them.
You have to have the base. It doesn't work because the bases aren't the same. You have to have the common base. These bases have to be the same in order to do any of that. That's why we can't combine them.
How is this thing that we end up any more useful than the thing we started with?
This is actually a simplified form of this.
But the
It still
answer
looks
is
like-
only on the bottom, not on the top, not the bottom.
Right.
Like, what difference does it make?
It's the exact. It's the etiquette way of doing it.
Etiquette way?
Yep.
And
It's all about
how does it make
It doesn't make anything cleaner, it doesn't make anything easier, it's just the right way to do it.
So somebody was like, the answer has to be on the top, that's...
As we go on to this one, I have the 4th root of 80 over 9. 4th root of 80 over 9. In this example here, I obviously cannot simplify that fraction. So, and then I'm going to sit there and think, okay, is there a perfect 4th root of 9? No. But 9 can be rewritten as 3 squared, though, correct? Okay. What about 80? What can I break 80 into?
8 times 10.
8 and 10? All right. What is a perfect square, though? 4 goes into it, right? Does 16 go into it?
Yeah.
It's 16 and 5, right?
Since you said that.
If it's 16, isn't that 2 to the 4th power? So let's do this. This is, it was 2 to the 4th was 16 times 5, right? You okay with that?
Oh, it is there.
All over 3 squared? Is everybody okay with that? If I distribute that 1/4 power to everything, you wind up with 2 to the 4/4, 5 to the 4th, over 3 to the 2/4. Are you okay with that? How do you multiply?
Pretty good.
So 2 to the 4/4 is what? Just plain old 2.
Yeah.
So this is 2 times 5 to the 4th over 3 to the half. What do you have to multiply top and bottom by now?
Oh.
The half?
3 to the half power. Does that make sense?
Yeah. 3 to the
No?
half. That makes sense.
Oh, okay. What happened here was we couldn't do anything to start with. But we look at the 80, we look at the 9, we break it down into some of our fundamental bases. We rewrite them in terms of squares, cubes, fourths, things like that. We were able to. 16 and 5. 2 to the 4th times 5. Now, multiply top and bottom by 3 to the half.
It's like the fourth root of 5 and the cube root and the square root of 3.
Yes, sir. Now, when I finish this out, 3 to the half times 3 to the half is just plain old boring 3. You okay with that? The numerator becomes 2 times the fourth root of 5 times the square root of 3. And it just looks really, really, really weird. And that's okay. Things look weird from time to time. It happens.
Like, is this some kind of speech to like?
Wait, how did you multiply 2 times 5 to the 1/4?
I didn't. I put it together.
Oh,
I can't. There's nothing I can do about it.
how do you know when to stop then?
Is there any radical in the denominator? It's a great question, guys. It's a great question. How do you know when to stop?
You just can't.
In this, you just don't give up. In this case, we have no radical in the denominator, and there's nothing else in the numerator that can really simplify it. You're not gonna cry.
Oh, you really are.
All right.
Yeah, I tried.
So.
The never-ending math problem.
The never-ending math problem.
Something like that. It takes time.
I'm sure there is. In this case here, we have the cube root of 4 divided by the fifth root of 8. Those guys are very, very close to having the same base. Do you agree? Let's rewrite these things, both numerator and denominator, as having a base of 2 and a fractional exponent. I'm going to rewrite them to have a fractional exponent with a base 2. 4 can be written as 2 squared, but it's the cube root of 4, right?
So to the 1/3.
So can I say it's 2/3? Is it okay? Can I skip that and write it out twice? Correct. All right. I because that's how I used to write it as a mixed number, yes. Now, 8 can be written as what? 2 cubed. So the fifth root of 2 cubed is going to be 2 to the... Once again, I have the same base now, don't I?
Oh, 2 cubed.
2 cubed? 8.
Right.
So now, fight to the death. Who wins? 2/3 or 3/5? 2/3. So check it. What would you have to get? 15 is your common denominator.
The top wins, it's 115.
So up here you get, if this is 15, it's 10 over 15. Here is 9 over 15. So now you have the same base, different exponents you're dividing. You play war.
Yeah.
Common denominator between 2/3 and 3/5. 2, yep. But then, how did the problem start?
This makes sense now.
It's the 15th root of 2. It is stupid.
It really is.
What are the 5 numbers you multiply together to get 2? I don't know, but I bet you there's a decimal involved.
Yeah, I bet there isn't then.
What is it? Holy shit, with the asymptote on that mother function? What? Did I say something wrong?
No, you said something mathematically.
really fast.
I know, that's the point.
Error.
Error.
Syntax error.
Syntax error. All right.
404 error.
Wait, yes, 2 to the 115 is 1.0472.
All right, let's go to these last couple here, because believe it or not, when you work with variables, it's so much easier. Variables are so much easier.
Oh, yeah.
So you have 160 to the half power minus 10 to the half power. What does half power mean?
Square root.
Square root.
Square rooted.
In order to subtract 2 square roots, you have to have the same base. Remember that?
Yeah.
What's the perfect? What's the you're gonna do push-ups next time you say that. What is the perfect square that's hiding in 160?
16 and 4 to the root.
Yes, sir.
when we have fractions, why do we turn it into nth roots, and when we have nth roots, we turn it into fractions?
It makes your,
Like, why don't we just stick with what we have?
it's easier sometimes to break it apart, because here you're looking, because this means square root, you're just gonna simplify it, it's a little bit quicker. There are certain times you do, certain times you don't, it's just a matter of getting accustomed to what makes sense. There's no rhyme or reason here. So what's 4 root 10 minus root 10?
3 to 10 half. No, you gotta change the grade.
Can't you split that up?
Because, what's that?
The 10 more though, right? It's like the
Remember, it's very common people do that. That's 4x minus x. That's not just 4. That's 3x.
There's too much stuff.
Now,
It's got to change back to a fraction.
oh, thank you. Notice, my original problem started as a fractional exponent, which means I have to finish within the fractional exponent.
I can die right now.
All right. And then lastly, I'm looking at the cube root of 375 and the cube root of 81.
Oh, yeah.
We know that 81 was how many 3's?
Oh, 4.
All of them, yes. 4 of them, right? So what's 3 3's?
27.
Like 27.
That's like right.
That's like Jinkies. Rad.
So the cube root of 27 times the cube root of 3 to simplify out the 81. 375. Gee, I wonder what might be hiding in there.
125.
125, right, correct.
Why is that good?
What's the cube root of 125?
5.
What's the cube root of 27?
3.
What's 5 plus 3?
9.
I don't know how to change back.
And you're done. You're simplifying working these through.
Are you?
I am so lost.
Mine keeps us to like 30.
Man, I got a lot further than that earlier classes too.
Actually, you have a lesson.
Yeah, I had
Like,
stuff to do, so you guys just
brain
don't have to
is
do it.
bleeding.
That's great. It's an honors algebra 2 class, and this is what everybody goes through. It's even the algebra 2 classes do this stuff, guys. This is the same thing that they're gonna see it as well. All right, you guys should be ahead of the curve, and it shouldn't be this painful. Okay, it's just adding and working with fractions. It's number sense. It's looking at something and identifying what I explained to you guys. My expectation. You got to know your cubes. You got to know your fourths through like 3, 4, and 5. There are not that many of them. They're very easy to work with. I know this is only the first couple times you've seen some of this, and it takes a while to get accustomed to seeing it. But it's the exact same process as what you went through with square roots. Instead of looking for squares, you're looking for cube. And you just start working through it. The process doesn't change. It's breaking into the base values, combining like terms. It's really all this is. Okay? It's really all it is. When it gets into your variables, and I know we kind of talked a little bit about the division problem last week, right? How fast that is to do the fourth root of the whole monomial. How many times to go in, take stuff out. We did that one, right? No, I thought we did.
We have one problem.
We did this one, right? Where 4 goes into 5 how many times? Once, and you just kind of go through that. Just for a refresher, is there a perfect fourth root of 10? No. So we have this, we left it up to the fourth root of 10. Then we did that quick little division game. 4 went into 5 how many times? 1 came out and 1 stayed in. We vaguely remember this now? 1 came out, 1 stayed in. 4 goes into 8 how many times? Twice. 2 come out, there's nothing left. 4 goes into 10 how many times? 2 go out, 2 stay in.
Oh, that's pretty self-explanatory.
How many times is 4 going to 10? That's why.
So 2 going to
Yep. If this was z to the 11th, 4 goes into 11 twice, 2 out, 3 stay in. If it was 12, Correct.
Oh, that's pretty simple.
And that's all that was. Okay? Sorry, I just got something in my eye. I can't talk.
I can't talk, there's something.
I can't talk, there's something in my eye. All right.
I can't see you, it's so loud.
Oh, yeah.
That's what I call them.
And then the other part of this I want to just kind of briefly show you is how much easier this becomes when it's just variables. You don't have to worry about trying to find that perfect cube root, that fourth. All you're doing is you're playing games of war and you're working through your exponent rules of adding or subtracting, maybe even multiplying. When we've done large monomial style problems in the past with the exponent rules, I've always said go variable by variable before you do anything. So here I have x to the 3/4 over x to the 4th. It's a game of war, isn't it?
Yeah.
Who wins? 3/4. X to the 3/4 wins. So it gets x to the 2/4, which is 1/2. I'm just going to leave it like that for right now, and I'll come back and simplify it at the end. If you want to do it, that's fine. I'm just going to take the long road to walk you through. Variable of y, there's just one of them. Just stays there. Z to the negative 1/3, z to the 2/3. That z to the negative 1/3 is not happy, is it?
No.
It's got to go. So it's z to the 2/3 times z to the 1/3. So what is it in the denominator? See how much easier it is with variables?
Yeah.
You're just working through the rules. You're playing the games of war and simplifying through.
Why do we learn numbers first?
Numbers are hard.
Yeah, and this seemed very tough on the pack.
Let's do one more. Now, it looks awful, but take a look. Aren't they all the same nth root?
Yes.
Make one giant nth root then. See that Y? Or did you see Y, W-H-Y? Now, in this scenario here, doesn't this denominator become y to the 12th?
Yes.
Can I just erase and do that? You're okay with that?
Yeah.
Now, who wins in the game of war? A 6 or a 12? 12. So this is the cube root of 1 over 27y to the 6th. You okay with that?
Yep. Yes.
All right. What's the cube root of 1? What's the cube root of 27? 3 goes into 6 how many times? 2. Any left over?
Well, wait, but you could have done it like not each one.
That was fancy.
It works either way. What happens a lot of times, if you recognize you have the same nth root, do that right away. It's just cleaner. Yes, ma'am.
And if they are the same,
Then you just go piece by piece. You go piece by piece to that problem we did a second ago where we just got to piecemeal them together. It's always easier to rewrite them if they're all different nth roots to go fractions. Okay? What I want you guys to do then is the same section. It's 412. I want you to do, what is this, 56 to 90 the evens. So it's the same section. Now, since we're dealing with just those variables, you're going to be very, very surprised at how fast it goes. It shouldn't be 15 minutes.
Gotcha.
I'm not lying. It really shouldn't. Okay? It'll 900 Venn. There's 900 Venns. You have 900 Venn diagrams to make.
Actually, it's 9 even.
It looks like it's a 90 oven.
90
90-degree oven.
90 degrees? What are you going to cook in a 90-degree oven? You can't even cook an egg at 90 degrees. An ice cube. How are you going to cook an ice cube? What value does that give you? Water. Do you need an ice cube to be melted to give you value?
All right, so excuse me.